Henderson Field, Guadalcanal, March 17, 1943. Staff Sergeant James Newell stood in the pre-dawn darkness, staring at the belly of an F-4U Corsair that wasn't supposed to be there. The fighter had landed 2 hours earlier, its pilot screaming over the radio about Japanese positions that needed bombing. But the Corsair wasn't a bomber, it was a pure fighter. 6 .50 caliber machine guns in the wings, nothing else. No bomb racks, no hardpoints. Just speed and firepower built into the most powerful single-engine fighter America had ever produced. The pilot, a Marine lieutenant named Davidson, was still arguing with the squadron commander 50 yards away. His voice carried across the flight line over the sound of distant artillery from the jungle perimeter. They needed dive bombers. They had fighters. And somewhere out there in the darkness, Japanese troops were massing for another assault on the airfield that had become the most contested piece of real estate in the Pacific. Newell had been a civilian mechanic in Detroit before the war. He'd worked on everything from Model Ts to Packards, and he understood something the military brass often forgot. An airplane was just a machine, and machines could be adapted if you understood their language. The Corsair spoke to him in rivets and aluminum, in hydraulic lines and stressed metal, and right now it was telling him something the engineering manuals never mentioned. This fighter had been designed to carry bombs. The Navy just hadn't built the hardware to let it do so. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem wasn't theoretical, it was immediate and lethal. VMF 124, the first Marine Corsair squadron to reach Guadalcanal, had arrived in February with aircraft that could outrun, outclimb, and outfight anything the Japanese had. The bent-wing birds, as pilots called them, had already proven themselves in air-to-air combat. Kenneth Walsh had just become the first Corsair ace. The fighters were winning the battle for the sky, but winning in the air didn't mean victory on the ground, and that's where the Marines were bleeding. Japanese positions dotted the ridgelines surrounding Henderson Field. Artillery emplacements, machine gun nests, mortar teams dug into coral limestone so hard it could turn a direct bomb hit into a near miss. The Douglas SBD Dauntlesses, the Navy's dedicated dive bombers, were doing what they could, but there weren't enough of them. Requests for more bombers got lost in the logistics pipeline somewhere between Pearl Harbor and the Solomons. Meanwhile, 18 Corsairs sat on the flight line, and 18 frustrated pilots watched positions they could see but couldn't strike. The Navy had never intended the Corsair for ground attack. The F-4U had been conceived in 1938 as a pure interceptor, built around the most powerful engine Pratt & Whitney could produce. The R-2800 Double Wasp pushed over 2,000 horsepower through a 13-foot propeller, the largest ever fitted to a fighter. To get ground clearance for that massive prop without using landing gear so long it would collapse on carrier decks, Vaught's engineers had designed the distinctive inverted gull wing. Every decision in the aircraft's design prioritized one thing: speed. The Corsair had been the first American fighter to exceed 400 miles per hour in level flight. Bombs had never been part of the equation. The original design included provisions for 2 small anti-aircraft bombs under the wings, meant to suppress shipboard flak during attacks on Japanese carriers. But those racks had been deleted in production models when the Navy decided fighters needed more ammunition instead. The centerline, where a bomb rack would naturally mount, was occupied by a massive 237-gallon fuel tank positioned directly ahead of the cockpit. There was no room, no mounting points, no engineering documentation. Building a bomb rack for the Corsair would require redesigning the airframe, a process that would take months and require approval from Vought, from the Bureau of Aeronautics, from procurement officers who'd never seen mud and blood at Henderson Field. Newell didn't have months. He had until sunrise, when Davidson's flight was scheduled to escort another bomber mission. The Japanese would shoot at the bombers and ignore the fighters, because fighters couldn't hurt ground targets. It was an equation that made tactical sense but felt morally wrong to everyone. Watching Marines die under artillery fire, they couldn't silence. He walked the flight line as the first grey light touched the eastern horizon. Mechanics were already warming up engines, that distinctive whistle of air through the Corsair's cowl flaps cutting through the morning. The sound had given the aircraft its Japanese nickname, Whistling Death. But right now, the death was mostly theoretical. Newell needed to make it practical. The centerline was the obvious location for a bomb rack. Directly under the fuselage, on the aircraft's center of gravity, a single large bomb could be carried without affecting flight characteristics significantly. But that space was occupied by fuel plumbing and structural reinforcement for the main landing gear. You couldn't just bolt a rack to the aluminum belly and hope it held. A 1,000-pound bomb created forces that would tear through aircraft skin like paper if the attachment points weren't engineered correctly. But Newell had noticed something 3 days earlier, while replacing a damaged belly panel on a different Corsair. The fuselage had hardpoints, reinforced attachment locations built into the airframe structure. They were designed for mounting tie-down rings when the aircraft was transported by ship, simple metal eyes that let deck crews secure the fighters during rough seas. The hardpoints were over-engineered for that purpose, stressed to handle loads far exceeding what they'd normally see, which meant they might, possibly, handle something else entirely. He pulled the technical drawings from the maintenance tent. Working by flashlight, he traced the load paths through the Corsair's structure. The tie-down hardpoints were positioned almost perfectly for a centerline rack. They aligned with the fuselage's main strength members, the heavy longerons that ran the length of the aircraft. If he could build a rack that attached to those existing hardpoints, the loads would feed directly into the airframe's strongest components. The question was whether those hardpoints could handle the dynamic loads of a bomb release at 300 miles per hour in a steep dive. The math was ugly. Newell wasn't an engineer with slide rules and stress calculations. He was a mechanic with experience and intuition. But he understood leverage and material strength from years of looking at broken parts and figuring out why they'd failed. The tie-down hardpoints were quarter-inch steel plate, through-bolted to the longerons with grade 8 hardware. Each hardpoint was rated for at least 2,000 pounds of static load. A 1,000-pound bomb, hanging stationary, would split that load across multiple attachment points, maybe 400 pounds per hardpoint, well within limits. But dynamic loads were different. When the pilot released the bomb, there'd be an impulse load as the bomb separated from the rack. When the aircraft pulled out of its dive, G-forces would multiply the bomb's weight. 3 Gs would turn a 1,000-pound bomb into 3,000 pounds of force, trying to tear the rack off the airframe. The hardpoints might hold. Or they might rip through the fuselage skin, turning the Corsair into an uncontrolled ballistic object at 4,000 feet. Newell made a decision that would either save lives or end his career. He was going to build the rack. The immediate problem was hardware. You couldn't fabricate a bomb rack from scratch on Guadalcanal. There were no machine shops, no mills, no lathes capable of precision work. What they had was a salvage yard full of crashed aircraft, a welding rig that worked when the generator cooperated, and whatever creativity desperation could provide. The answer came from an unexpected source. A Brewster SB-2, a Buccaneer, a dive bomber so terrible it had been withdrawn from service before seeing combat. 3 of them had been abandoned on Guadalcanal after mechanical failures. The Navy had no spare parts to fix them, and nobody wanted to anyway because the aircraft was a death trap. But death traps sometimes had useful components, and the Buccaneer had a very good bomb rack. Newell and 2 other mechanics spent 4 hours in the tropical heat, cutting the centerline bomb rack assembly out of a wrecked Buccaneer. The rack was a Brewster design, elegant in its simplicity. A series of steel arms that cradled a bomb with a pneumatic release mechanism triggered by the pilot. The attachment points were completely wrong for the Corsair's fuselage, but the core mechanism was sound. If he could adapt it, modify the mounting brackets, and figure out how to attach it to those tie-down hardpoints, it might work. The modification took shape in his mind, before his hands started cutting metal. The Brewster rack's main support beam was a steel channel, about 4 inches deep, running the length of the bomb. He could cut away the Buccaneer-specific mounting flanges and weld new brackets directly to that channel. The new brackets would have holes matching the Corsairs' tie-down hardpoint positions. Long-grade 8 bolts would pass through the brackets, through the fuselage skin, and thread into the hardpoint plates. The bomb's weight would hang from the channel, which would transfer loads through the brackets to the hardpoints, which would transfer them into the longerons. It was mechanically sound, probably. The welding was the critical part. Newell had welded before, but aircraft-quality welds were different from automotive work. Too much heat and you'd weaken the steel. Too little and the weld wouldn't penetrate. The brackets had to be perfect because there'd be no second chance. If the rack failed in flight, the investigation board would trace it back to whoever signed off on the modification. He worked through the night. The island's generator provided intermittent power to the welding rig. Between power failures, he measured twice, cut once, and assembled the modified rack on the maintenance tent's concrete floor. By 0400, he had something that looked like it might work. By 0500, he'd test-fitted it to the Corsair Davidson would fly. The physical installation was straightforward. 4 long bolts through the fuselage skin, threading into the tie-down hardpoints, lock wire on every fastener, because vibration would shake anything loose that wasn't secured. The pneumatic release line from the Brewster rack had to be adapted to connect with the Corsair's hydraulic system, using a quick disconnect fitting salvaged from a damaged landing gear strut. The electrical trigger went to the bomb release button on the pilot's stick, with a simple relay to convert the electric signal to pneumatic pressure. At 0600, with the sun fully up and the morning patrol already airborne, Newell walked to the operations tent where Davidson and the squadron commander were still arguing about mission profiles. "Sir," Newell interrupted, knowing enlisted men didn't interrupt officers, but also knowing Marines forgave breaches of protocol when they solved problems. "We can hang 1,000-pounder on that Corsair." The silence lasted about 3 seconds. "Show me," the commander said. They walked to the flight line together, Davidson practically running to keep up. The Corsair sat in its revetment, coral dust coating the dark blue paint. Underneath the fuselage, visible in the morning light, hung the modified Brewster bomb rack. It looked wrong, improvised, exactly like what it was. A Navy officer with peacetime sensibilities would have rejected it immediately as non-standard equipment installed without proper authorization. "Did Vought authorize this?" the commander asked. "No, sir. I built it last night using parts from a wrecked Buccaneer. The attachment points are the tie-down hardpoints. They're strong enough if the pilot doesn't exceed 4 Gs in the pullout." "If? What happens at 5 Gs?" "I don't know, sir. Probably nothing. Possibly something catastrophic." Davidson was already doing a walk-around inspection, his hands tracing the rack's mounting points. "This is either brilliant or insane." "Both," Newell said. The commander looked at the fighter, at the rack, and at the ridgeline where Japanese artillery had started its morning bombardment. Shells were landing near the eastern perimeter. Marines were dying while officers debated engineering tolerances. "Load it," he said. "1 bomb. If it works, we'll put racks on every Corsair we've got." "And if it doesn't work?" Davidson asked. "Then we'll have learned something about metallurgy. Load the bomb." 30 minutes later, a 1,000-pound AN/M65 general-purpose bomb hung beneath the Corsair's belly. The aircraft sat lower on its landing gear, the added weight compressing the oleos by several inches. Ground crew had painted experimental on the bomb in white chalk, as if labeling it would somehow make the improvisation more official. Davidson completed his pre-flight check. Fuel full. Oil pressure good. Hydraulics responding. All 6 machine guns loaded. And underneath, hanging from a rack that hadn't existed 12 hours earlier, enough high explosive to erase a Japanese bunker from existence. "Ground control," Davidson radioed. "Corsair 47 requesting permission to taxi for strike mission." 47, be advised you're not on the schedule for strike." Ground control, I'm carrying ordnance. Somebody should probably mention that to the tower. There was a pause. Then a different voice, the air operations officer. 4-7, confirm you're carrying bombs. Corsairs don't carry bombs. Sir, this one does. Request permission to prove it. Another pause. Longer this time. 4-7, cleared to taxi. Try not to blow yourself up. We're short on pilots. Davidson advanced the throttles. The Pratt & Whitney roared, that 18-cylinder radial pushing 2,000 horses through the propeller. The Corsair rolled forward, handling normally despite the external load. The bomb hung stable underneath, the rack showing no signs of stress. So far, Newell's midnight engineering was holding together. The tower cleared Davidson for immediate takeoff. No time for proper procedures. Japanese scouts had reported a concentration of enemy forces preparing for another assault on the American perimeter. The target was a tree line about 6 miles northwest, where aerial reconnaissance had spotted camouflaged artillery positions. If the Corsair could hit it, Marines wouldn't have to assault it. Simple math written in human lives. Davidson pushed the throttle to full power. The Corsair accelerated down Henderson Field's steel matting, the added weight of the bomb requiring slightly more runway than normal. The fighter lifted off at 115 indicated airspeed, climbing strongly, despite carrying ordnance it was never designed to carry. The landing gear retracted cleanly. The bomb remained attached. Newell, watching from the flight line, allowed himself the first full breath since the aircraft had started rolling. The flight to the target took 8 minutes. Davidson climbed to 6,000 feet, giving himself room for a proper dive bombing run. The Corsair handled differently with the external load, slightly nose-heavy, requiring constant trim adjustment, but it flew. That was what mattered. Through the windscreen, Davidson could see the target area. A tree line along a ridgetop, looking innocent from altitude but known to conceal at least 3 Japanese 75mm guns that had been pounding Marine positions for a week. The bombers had tried to hit it. The artillery had missed it. Now, it was his turn with a fighter that was supposed to be killing enemy aircraft, not enemy gun crews. He rolled inverted and pulled through, diving at 60 degrees. The airspeed indicator wound up rapidly. 200 knots, 250, 300. The Corsair was a stable diving platform, its heavy engine pulling the nose down naturally. But with a bomb attached, the aerodynamics changed subtly. Davidson had to correct with slight back pressure on the stick, keeping the target centered in his gun sight. 3,000 feet, 2,500. He'd been told not to exceed 4 Gs in the pullout, which meant releasing at around 2,000 feet and accepting whatever accuracy the physics allowed. 2,200 feet altitude, range decreasing fast. He thumbed the bomb release. The Corsair lurched upward as 1,000 pounds suddenly disappeared from its belly. The rack had held. The release mechanism had worked. The bomb fell away cleanly, tumbling through the morning air toward a target that had no idea a fighter had just become a bomber. Davidson pulled back on the stick, loading the airframe to 3.5 Gs. The Corsair arced out of its dive, the G-forces pressing him into his seat. He counted seconds. 1, 2, 3, 4. The explosion erupted below him, a fountain of earth and splintered trees and black smoke. The blast was centered directly on the tree line. Secondary explosions followed as stored ammunition cooked off. The Japanese artillery positions ceased to exist in approximately 1.2 seconds. Davidson keyed his radio. Ground control, 4-7, target destroyed. The rack worked, returning to base. On Henderson Field, Newell was already gathering his tools. They'd be working through the night again. 18 Corsairs needed bomb racks, and the Marines needed them by sunrise. The modification that had begun as an improvised solution to an immediate problem was about to change the war in the Pacific. Not because it was elegant or officially approved or properly documented, but because it worked. And in combat, working was the only standard that mattered. The news spread through Henderson Field faster than malaria. By noon on March 17, 1943, Every pilot on Guadalcanal knew that Davidson had just dropped a 1,000-pound bomb from a Corsair. By sunset, mechanics from 3 different squadrons were standing around Newell's modified bomb rack, asking questions he was still figuring out how to answer. The immediate reaction from the chain of command was predictable chaos. The operations officer wanted documentation. The engineering officer wanted stress calculations. The squadron commander wanted 5 more racks installed by morning. And somewhere in Pearl Harbor, a Bureau of Aeronautics desk officer would eventually learn that unauthorized modifications were being made to frontline aircraft without proper approval, engineering review, or any of the bureaucratic infrastructure that kept the Navy running in peacetime. But this wasn't peacetime, and Guadalcanal wasn't Pearl Harbor. The island operated on different rules, written in mud and urgency. If something worked, you used it. If it didn't work, people died. The approval process had been compressed to a single question: can you build more? If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Newell's answer was yes, but with complications. The Brewster racks could only be salvaged from wrecked aircraft, and there were exactly 2 more Buccaneers sitting abandoned near the airfield. That meant 3 bomb racks. Total. 3 Corsairs could be modified immediately. For the other 15 fighters in the squadron, they'd need a different solution. The problem was manufacturing capacity. Guadalcanal had a machine shop that consisted of 1 elderly lathe, a drill press that worked intermittently, and welding equipment powered by a generator that died whenever anyone looked at it wrong. The concept of precision manufacturing had died somewhere around the time Japanese artillery started landing near the maintenance area. What they had was scrap metal, cutting torches, and mechanics who'd learned to make do with whatever materials physics and desperation provided. The solution came from an unexpected direction. A Navy construction battalion, the famous Seabees, had a small fabrication facility near Lunga Point. They'd been building everything from Quonset huts to bridge supports, working with structural steel and heavy equipment. Their welding capabilities were far beyond what the aircraft mechanics had access to. More importantly, their commanding officer was a former construction foreman from Pittsburgh who understood that regulations existed to serve the mission, not the other way around. Commander Frank Ibbotson walked the flight line on March 18th, examining the modified Corsair that Davidson had flown. He was 42 years old enough to remember the First World War, and young enough to understand this one was different. Industrial war required industrial solutions, and the Seabee motto was, "We build, we fight." Right now, building meant turning fighters into bombers. "You need 15 of these," Ibbotson asked Newell. 18 total. We have 3 working, need 15 more. What's the design? Newell showed him the sketches he'd drawn on the back of a maintenance form. They weren't engineering drawings. They were mechanics' shorthand, showing dimensions and load paths and attachment points in a language that anyone who'd worked with metal could understand. Ibbotson studied them for about 90 seconds. "We can build these. Give me 3 days. We need them faster than 3 days. Then you'll get them in 2 days, and they'll be ugly. But they'll hold together." The Seabees worked in shifts, fabricating bomb racks from steel plate and angle iron. The design was brutally simple: 2 longitudinal steel channels running parallel, connected by cross members, with mounting brackets at 4 points that matched the Corsair's tie-down hardpoints. The bomb cradle used spring-loaded arms that gripped the bomb's suspension lugs, released by a pneumatic cylinder salvaged from bulldozer hydraulics. It wasn't elegant. It was heavy, adding an extra 40 pounds compared to the Brewster design. But it was strong, probably overbuilt, and most importantly, it could be manufactured with the tools they had available. By March 20th, 15 new bomb racks sat outside the Seabee workshop, waiting to be installed. They looked nothing like production hardware. The welds were agricultural, thick beads that said, "This will never fail," rather than "This saves weight." The steel was painted in whatever color had been available, resulting in racks that were grey, green, and in one case, bright yellow from construction equipment paint. But each rack had been load tested to £1,500 before leaving the fabrication shop. They'd hold. Installation began immediately. Newell trained 8 other mechanics on the process. Drill holes through the fuselage skin at the hardpoint locations. Bolt the rack in place with grade 8 hardware. Connect the pneumatic release line to the aircraft's hydraulic system. Wire the electrical trigger to the bomb release button. The procedure took about 4 hours per aircraft if nothing went wrong, and about 8 hours when things went wrong, which was most of the time. The hydraulic connections were the persistent headache. The Corsair's hydraulic system operated at 3,000 psi, far higher than the pneumatic pressure needed for the bomb release. Engineers would have designed a proper regulator, reducing pressure through calibrated orifices and safety valves. The mechanics didn't have proper regulators. What they had was a hydraulic pressure switch from a damaged landing gear system set to trigger at 800 psi, which fed a small pneumatic reservoir that then powered the release cylinder. It was mechanically sound but artistically terrible, the kind of solution that worked perfectly until it didn't. By March 23rd, all 18 Corsairs in VMF 124 had been modified. They sat on the flight line looking like pregnant seabirds, bombs hanging underneath bellies that had never been designed for external stores. The pilots loved it. The engineering officers hated it. The Marines getting shot at by Japanese artillery didn't care about the aesthetics. The first full squadron strike happened on March 24th. 18 Corsairs, each carrying a 1,000-pound bomb, launched in 2 divisions against Japanese positions near Cape Esperance. The target was a supply dump that aerial reconnaissance had identified, camouflaged under jungle canopy but visible from specific angles when the sun was right. Traditional bombers had missed it twice. The Corsairs would get one chance. Lieutenant Kenneth Walsh led the 1st Division. He'd become famous for his air-to-air victories, the first Corsair ace. But now he was leading a bombing run in an aircraft that was still learning how to do this. The formation climbed to 8,000 feet, giving themselves altitude for proper dive angles. Below them, Guadalcanal looked peaceful from this height. The jungle was green, the beaches were white. Nothing indicated that people were dying down there over patches of mud that wouldn't matter to anyone once the war ended. Walsh rolled into his dive at 70 degrees, steeper than Davidson's earlier attack. The Corsair accelerated rapidly, wind noise building to a scream, through the airframe. At 4,000 feet, he released. The bomb separated cleanly, the rack performing exactly as Newell had promised. 17 more Corsairs followed him down, one after another, each releasing at slightly different altitudes as pilots adapted to individual aircraft quirks and personal risk tolerance. 18,000-pound bombs hit an area roughly 200 yards square in approximately 90 seconds. The Japanese supply dump, which had survived 2 previous bombing attempts, ceased to exist. Secondary explosions continued for 15 minutes as ammunition and fuel stores detonated in a cascade of sympathetic explosions. Reconnaissance photos taken the next day showed a crater field where jungle had been, with nothing left intact larger than a small tree. The success created an immediate problem. Demand for bomb-carrying Corsairs exceeded supply. VMF 213, the 2nd Marine Corsair Squadron on Guadalcanal, wanted their aircraft modified immediately. So did VMF 221. And Navy Squadron VF-17, operating from Munda, sent a formal request asking for technical specifications so their mechanics could duplicate the modification. The cat was out of the bag, and the cat was now dropping high explosives on Japanese positions across the Solomon Islands. Newell found himself in the unexpected position of being a technical consultant to multiple squadrons. He wasn't an engineer. He didn't have formal training in aircraft modification, but he'd solved a problem that Vort's engineers hadn't anticipated and the Bureau of Aeronautics hadn't authorized, and now everyone wanted to know how he'd done it. The technical specifications, such as they were, got written on a dozen sheets of notebook paper, dimensional drawings showing hardpoint locations, sketches of the rack's basic structure, notes about hydraulic pressures and electrical connections. It wasn't proper documentation. It was a mechanic's guide to building something that worked, written in language that other mechanics would understand. The specifications got copied and recopied, passed from squadron to squadron, showing up in maintenance tents from New Georgia to Bougainville. The modifications spread through the Pacific theater like a virus, but viruses mutate, and so did the bomb rack design. Mechanics at different bases made their own improvements based on available materials and local conditions. The squadron at Munda developed a stronger mounting bracket using steel from a wrecked Japanese Zero. Engineers at Espiritu Santo fabricated racks from aluminum instead of steel, saving £60 per aircraft at the cost of requiring more careful handling. A maintenance chief on New Britain figured out how to adapt the rack to carry two 500-pound bombs instead of 1,000-pounder, doubling the number of targets a single Corsair could attack. Each variation moved further from Newell's original design, but they all shared the same core concept. Use the existing tie-down hardpoints. Keep the weight on the center of gravity. Don't exceed 4 Gs during pullout. The specifics varied, but the principles remained constant because physics didn't care about individual creativity. The official response from the Bureau of Aeronautics arrived in early April. A tersely worded message directed to all squadrons operating F-4U aircraft, informing them that unauthorized modifications were prohibited, that all aircraft must conform to standard configuration, and that any deviation required formal engineering review and approval from BUA in Washington. The message was read, acknowledged, and then quietly ignored. By the time it arrived, over 50 Corsairs across the Solomon Islands had been modified with improvised bomb racks. Pilots were flying multiple combat missions per day, striking targets that had previously required dedicated dive bombers. Marine infantry advancing through the jungle had close air support from fighters that could arrive faster, stay longer, and hit harder than anything else in the inventory. Telling them to remove the racks and wait for official approval was like telling them to fight with one arm tied behind their backs. The squadron commanders responded with carefully worded reports, explaining that the modifications were temporary field expedients necessitated by tactical requirements, and would of course be removed as soon as official bomb racks became available. Everyone understood this was bureaucratic theatre. The racks weren't temporary, they were permanent, until something better came along, and nothing better was coming soon. What did come was official interest from the right people. A team from the Naval Aircraft Factory in Philadelphia arrived in late April to inspect the field modifications. They were engineers, not bureaucrats, and they understood the difference between breaking regulations because you were lazy and breaking regulations because you were solving problems. They examined Newell's original Brewster rack installation, photographed it from every angle, measured dimensions, and conducted load tests that confirmed what combat had already proven. The design worked. Their report back to Washington was unequivocal. The field-modified bomb racks were structurally sound, properly engineered within the limitations of available materials, and operationally necessary. The report recommended that an official centerline bomb rack be developed for the F-4U-1, incorporating lessons learned from the field modifications, but produced to proper manufacturing standards. More importantly, the report recommended that Staff Sergeant James Newell be formally recognized for solving a critical operational problem using available resources and mechanical ingenuity. The recognition never came. Newell's name appeared in maintenance logs and a few squadron reports, but enlisted mechanics didn't get medals for improvising solutions that should have been engineered from the beginning. He continued, working at Henderson Field through the summer of 1943, training other mechanics, refining the rack design, and maintaining the growing fleet of bomb-carrying Corsairs that were slowly pushing the Japanese back through the Solomon Islands. By June 1943, Vought had produced an official F-4U-1D variant, featuring factory-installed bomb racks under the wings and centerline. The company's engineers had developed proper mounting hardware, stress-tested to handle loads far exceeding anything Newell's improvised racks would see. The production racks were lighter, stronger, and properly integrated with the aircraft's hydraulic and electrical systems. They were everything a field modification wasn't: elegant, documented, approved. But they arrived 6 months late. 6 months during which Marines had needed bomb-carrying Corsairs and improvised racks had provided them. 6 months of combat operations that wouldn't have happened if mechanics had waited for official solutions to filter through the procurement system. The F4U-1D was a better aircraft than the field-modified F4U-1, but better late is still late. The Corsair's transformation into a fighter bomber changed the Pacific Air War in ways that took years to fully understand. Before the bomb racks, the Marine Corps operated with a clear division of labor. Fighters fought other fighters. Dive bombers hit ground targets. The system worked, but it required careful coordination and left fighters underutilized whenever air superiority had been achieved. With bomb-carrying Corsairs, that division dissolved. A single aircraft could escort bombers, fight enemy interceptors, and then strike ground targets on the return flight. The operational flexibility was revolutionary. The numbers told the story. Between March and August 1943, Corsairs in the Solomon Islands flew over 8,000 combat sorties. Before the bomb rack modifications, approximately 60% of those sorties were pure fighter sweeps or bomber escorts. After the modifications, that ratio inverted. 65% of Corsair sorties involved ground attack missions, delivering over 3,000 tons of bombs on Japanese positions. The fighter that had been designed to kill enemy aircraft spent most of its combat life killing enemy soldiers, destroying supply dumps, and cratering airfields. The Japanese noticed. Intelligence reports captured later in the war included references to American fighters attacking with bombs, something Japanese commanders initially dismissed as mistaken identification. When reconnaissance confirmed that single-engine fighters were indeed conducting dive-bombing attacks, the Japanese tactical response had to adapt. Anti-aircraft positions that had focused on defending against high-altitude bombers now had to account for fighters coming in fast and low. The defensive problem became geometrically more complex. The true measure of the modification's success came from an unexpected source. In August 1943, Major Gregory Boyington arrived at Guadalcanal to take command of VMF 214, soon to be famous as the Black Sheep Squadron. Boyington was an experienced pilot, aggressive, bordering on reckless, and completely uninterested in anything that didn't contribute to killing the enemy. He inspected the bomb-carrying Corsairs with the critical eye of someone who'd flown everything from P-42s in China to whatever he could steal in between. His assessment was blunt and positive. If I can put a bomb on a Japanese gun position and still have ammo left to shoot down fighters on the way home, that's the only kind of airplane worth flying. Boyington's squadron would go on to destroy or damage over 200 Japanese aircraft, using those same bomb-equipped Corsairs. The distinction between fighter and bomber had become meaningless. They were simply weapons platforms that could adapt to whatever the tactical situation required. And that adaptability traced directly back to a mechanic who'd decided that regulations mattered less than results. Newell rotated back to the United States in October 1943. He'd spent 8 months on Guadalcanal, survived malaria twice, and personally installed or supervised the installation of bomb racks on over 100 Corsairs. He received no medals, no commendations, no recognition beyond a "well done" from his squadron commander, and handshakes from pilots whose lives he'd probably saved by giving them better tools for an impossible job. He returned to Detroit after the war, went back to fixing cars, and never spoke much about his time in the Pacific. The Corsair became one of the war's most iconic aircraft, famous for its distinctive gull wings and its 11-to-1 kill ratio against Japanese fighters. But in the official histories, the aircraft's development into a fighter bomber was described as a natural evolution, a planned modification that emerged from Vaught's engineering department. The field modifications that had actually made it happen got lost in the paperwork. The bomb racks themselves continued evolving. The F4U-1D's official racks were improved in the F4U-4, which added capacity for rockets and even the massive Tiny Tim unguided missiles. By the Korean War, Corsairs were carrying 4,000 pounds of ordnance, far exceeding anything Newell had imagined possible when he'd cut apart a Brewster rack in the middle of the night on Guadalcanal. The aircraft flew until 1969, when a Honduran pilot scored the last propeller-driven fighter kill in history, shooting down an enemy Corsair in what historians would call the football war. The F-4U's longevity came from its adaptability, and that adaptability started with mechanics who understood that aircraft were tools to be modified rather than sacred objects to be preserved in original configuration. Newell's contribution was recognizing that the Corsairs' tie-down hardpoints could serve a purpose beyond their original design. That single insight, implemented with scrap metal and improvised hydraulics, changed how the Marine Corps fought in the Pacific. Part 3 Final Section. The broader lesson took decades to learn, or perhaps to remember, because the military had learned it before and forgotten it repeatedly. Innovation in combat doesn't wait for approval from headquarters. It happens when someone close to the problem has the skill and authority to implement solutions faster than the procurement system can deliver them. Newell had that skill. More importantly, his commanders had the wisdom to let him use it. The contrast with peacetime development was stark. The F-4U Corsair had taken 3 years from initial design in 1938 to first flight in 1940. It took another 2 years to reach operational squadrons. 5 years total for an aircraft that was desperately needed from the moment Pearl Harbor burned. The bomb rack modification, from concept to combat use, took less than 24 hours. The difference was necessity, proximity to the problem, and freedom from bureaucratic oversight. Modern military development hasn't entirely learned this lesson. The F-35 Joint Strike Fighter, conceived in the 1990s, didn't reach operational capability until 2016. 20 years from concept to deployment, longer than the entire Second World War. The aircraft is magnificent, capable of things Newell couldn't have imagined. But it's also a reminder that complexity and perfection come with costs measured in time, and time in combat means lives. The Marine Corps, to its credit, has institutionalized some of what Guadalcanal taught. Rapid fielding initiatives now exist to get new capabilities to Marines faster than traditional procurement allows. The philosophy is explicitly stated in modern doctrine. Put something that works in the hands of Marines today, rather than something perfect in their hands years from now. It's the same calculation Newell made when he decided that an improvised bomb rack was better than no bomb rack. But institutional memory is fragile. The mechanics who built those first racks are gone. The pilots who flew them are mostly gone. The squadron commanders who authorized the modifications without proper approval are gone. What remains are the aircraft in museums, restored to pristine condition, often without the field modifications that made them effective. The Corsairs at the National Museum of Naval Aviation and the Smithsonian are beautiful, historically accurate representations of the F-4U-1 as it rolled off Vaught's production line. They don't show the improvised racks, the salvaged parts, or the agricultural welds that characterized aircraft that actually fought. That sanitation of history matters because it obscures how wars are actually won. The narrative we preserve is that American industrial might and engineering excellence defeated the Axis powers. That's true, but incomplete. What actually defeated the Axis was American industrial might and engineering excellence, combined with thousands of James Newells who improvised solutions when official answers came too slowly. The mechanics matter. The welders matter. The supply sergeants who scrounged parts matter. They don't get monuments or history books, but they won the war just as surely as the pilots who flew the missions and the generals who planned the campaigns. The specific innovation of the Corsair bomb rack was relatively minor in the scope of the entire Pacific War. One modification to one aircraft type, affecting perhaps 500 aircraft out of the thousands that fought. But it exemplified a principle that scaled across the entire American war effort: adapt, improvise, make do with what you have. Fix problems at the lowest level possible, rather than waiting for solutions to filter down from headquarters. The Japanese didn't do this as effectively. Their industrial system was more rigid, more dependent on centralized planning and formal procedures. When Japanese aircraft needed modifications, the requests went back to the manufacturers, who submitted proposals to the Naval Air Technical Arsenal, which conducted reviews and eventually authorized changes that were implemented months later. The system produced excellent aircraft, but it produced them slowly, and it couldn't adapt to battlefield lessons as quickly as the more chaotic American approach. The German system fell somewhere between the two. German engineers were brilliant and innovative, but they were also perfectionists, constantly improving designs rather than building adequate numbers of good enough equipment. The Messerschmitt Me-262, the world's first operational jet fighter, was probably the most advanced aircraft of the war. It was also late, complicated, and produced in numbers too small to affect the war's outcome. Meanwhile, the Americans were building adequate fighters in overwhelming numbers and modifying them in the field to handle whatever the tactical situation required. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The F-4U Corsair ended World War II with a combat record that spoke for itself. 2,140 enemy aircraft destroyed against 189 Corsairs lost in air combat. An 11-to-1 kill ratio that made it the most effective naval fighter of the war. 15,621 tons of bombs dropped, 70% of the total bomb tonnage delivered by U.S. fighter aircraft in the Pacific. Those numbers came from an aircraft that had started the war as a pure interceptor and ended it as a multi-role fighter-bomber capable of anything from dogfighting to close air support. The transformation happened because a mechanic with a welding torch decided that regulations were less important than solving problems. James Newell never received the Distinguished Service Medal or the Legion of Merit. His name doesn't appear in the major histories of the Pacific War. The museum exhibits about the Corsair rarely mention the field modifications that made the aircraft effective in its most important role. But every Marine who got close air support from a bomb-carrying Corsair owed part of their survival to a solution that shouldn't have worked but did. That's the story that needs remembering. Not because it changes our understanding of major battles or shifts timelines of important campaigns, but because it reminds us that wars are won by ordinary people solving immediate problems with whatever tools they have available. The heroes aren't always the ones flying the aircraft or commanding the armies. Sometimes they're the ones in the maintenance tent at 0300, cutting metal and improvising solutions because the sun will rise in 3 hours and Marines will need bombs on target by 0700. Newell died in Detroit in 1984, 66 years old, from complications of the malaria he'd contracted on Guadalcanal 4 decades earlier. His obituary mentioned his military service in one sentence. It didn't mention the bomb racks. It didn't mention the hundreds of combat missions his modification had enabled. It didn't mention that he'd changed how the Marine Corps fought in the Pacific by recognizing that an aircraft's tie-down hardpoints could carry something more useful than tie-down rings. That anonymity was typical of the men who actually won the war. They didn't do it for recognition, or medals, or historical remembrance. They did it because it needed doing, and they had the skills to do it. And waiting for someone else to solve the problem wasn't acceptable when people were dying. That mentality, more than any specific weapon or tactic, was America's secret advantage in the Second World War. The Corsair flew on for decades after Newell's modification had been superseded by official production versions. It fought in Korea, dropping napalm on Chinese positions and providing close air support during the retreat from the Chosin Reservoir. It served with foreign air forces into the 1960s, long after jets had replaced propeller fighters in front-line service. The French Navy flew Corsairs in Algeria and Suez. The Honduran Air Force used them until 1979. Every one of those later aircraft incorporated lessons learned from the field modifications that had started on Guadalcanal. The official racks were better engineered and lighter, but they existed because mechanics had proven the concept was viable. The multi-role doctrine that made the F-4U valuable in Korea came from combat experience in the Solomons when fighters learned to carry bombs. The long service life happened because the aircraft was adaptable, and that adaptability had been demonstrated first by mechanics who refused to accept that fighters couldn't be bombers. The final Corsair combat mission was flown in July 1969 by Captain Fernando Soto of the Honduran Air Force, shooting down an enemy Corsair during the brief football war with El Salvador. Both aircraft were 25 years old, veterans of American service in World War II and Korea before being sold to Central American Air Forces. That two Corsairs fought each other a quarter-century after the type had entered service was testament to the design's durability and adaptability. But it was also testament to something less tangible. The F-4U had been designed for one mission and adapted to dozens. That flexibility came from treating the aircraft as a problem-solving tool rather than a finished product. The mentality that encouraged field modifications in 1943 was the same mentality that kept Corsairs flying effectively into the jet age. An aircraft, like any tool, exists to serve the mission. When the mission changes, the tool must change. Rigid systems that can't adapt eventually become irrelevant, no matter how excellent their original design. The lesson applies beyond military aviation. In any complex system, problems emerge that the original designers never anticipated. Those problems can be solved by sending them back up the chain of command, waiting for official solutions, and accepting whatever delays that process requires. Or they can be solved by the people closest to the problem, using their expertise and initiative and whatever resources are immediately available. The second approach is faster, messier, and usually produces solutions that offend anyone who values elegance over effectiveness. James Newell chose effectiveness. He built a bomb rack from scrap metal, installed it without authorization, and created a capability that changed how the Marine Corps fought. The rack wasn't elegant. It wasn't officially approved. It probably violated a dozen procurement regulations and engineering standards. But it worked. And in combat, working is the only standard that matters. 50 Corsairs in museums around the world preserve the aircraft's legacy. Restored examples fly at air shows, their distinctive bent wings and powerful engines reminding audiences of an era when American industrial might reshape the world. The aircraft are beautiful, mechanical art pieces that represent engineering excellence and manufacturing scale. But they're also sanitized, restored to factory specifications, missing the field modifications and improvised repairs that characterized aircraft that actually fought. Perhaps one should be different. One Corsair in one museum should be restored with a field-modified bomb rack, with agricultural welds and mismatched paint and salvaged parts that tell the real story of how wars are won. Not by perfect engineering and unlimited resources, but by ordinary people solving immediate problems with whatever they have available. That would be a monument worth building, not to glorify war, but to remember the mechanics and the welders and the supply sergeants who made victory possible. Staff Sergeant James Newell, United States Marine Corps, mechanic, problem solver, innovator. He built something that shouldn't have worked but did. The military gave him no medals. History barely remembers his name. But every Corsair that ever dropped a bomb flew because a mechanic in the South Pacific decided that rules mattered less than results. That's the most American story of the entire war.